Rene is a reader at the Jodrell Bank Centre for Astrophysics at the University of Manchester. He's been there since November 2014. He fell in love with astronomy when he was a little boy and spent countless nights stargazing and dreaming about becoming a professional astronomer while he was growing up. He was born and raised in Quebec City, Canada. He had a PhD from McGill University in 2009 under the supervision of a Vicky Caspi, and there's a link to the McGill Pulsar group if you find Rene's webpage. He was a research fellow at the University of Toronto and a member of Martin van Kerkhovik's group from 2008 to 2011. He was a research fellow at the University of Southampton in Rob Fender's 4Pi Sky group from 2012 to 2013, also a lecturer there from 2013 to 2014. And he tries to maintain a web page dedicated to the double pulsar. He was awarded a €2 million ERC starting grant in 2016. And who said that astronomers were poor? I hope you've still got some left anyway. Which grant started in March 2017, and this supports his research on a project called Fundamental Physics using Black Widow, Redback and Transitional Pulsar Binaries, and this is until the end of 2021. He also conducts some research in food security and runs a project called Parthenium in Pakistan, support by the Global Challenges Research Fund, which is aimed at tracking these invasive species on a large scale in order to help control its spread. And he works with scientists at the NGO called CABI, or is it CAB1? So
it's CABI, yeah.
Right, thank you. He's a multi-wavelength physicist, but he likes to think of himself as an observer and applied theorist, as a lot of his work lies in the frontier between observational science and theory. His research themes revolve around neutron stars and pulsars, transitions, binary systems, tests of gravity, and neutron star equation of state. He also does some digital instrumentation in the radio now. He enjoys practicing and watching sports in his spare time, and he keeps his mind and body sane. He likes a variety of them, such as running, hiking, volleyball, ice hockey, football, and really got into road cycling during his years in Toronto, which was about 2009. Other than that, he loves music, the listening bit, as he has no talent whatsoever to play, photography, geeking around with techno stuff, tea, coffee, wine, and many more things. Well, thank you very much, Rene, for all that information. Some will only give us a couple of lines, but I'm glad we know a little bit more about them. So please welcome Rene Breton. Thank you.
Thank you very much for the very kind introduction. Now I realize that I'm pretty much failing at some of the things you said because I'm not very good at updating the double pulsar webpage these days, nor my website or biography, but it doesn't matter. As Steve kindly told you, I'm an astronomer who works mostly on pulsars and neutron stars. However, the topic of my presentation tonight is about black holes. They're not the types of objects that I primarily study, but they're close enough actually to my field of research. And typically, regardless of what I talk about in a talk, usually in a public talk, I tend to have at least one question about black holes. So eventually I decided that, wow, I might as well give an entire talk about it and then see if I can get a question about pulsars for a change or something. So so let's see. By the way, it was mentioned as well that I do some research in remote sensing, and it's something I started a bit out of the blue, something like 2 or 3 years ago, because a colleague of mine, Sarah Bridle, who has now published a really good book about the effect of our food habits on global warming and the likes. And so she started this network putting in touch astronomers and mathematicians with people who work in agriculture and fields connected to the food, all from the farm all the way to supermarkets. And so I linked up with these people at CABI, and we set up this project to look for a really nasty plant that's called Parthenium, and it spread in Pakistan and India, but also in many other countries, for instance, in Kenya and other countries of Africa. And it destroys like the crops there. And a lot of these, countries are currently, developing countries. So you can imagine a smallhold farmer, having their crops destroyed, it's very bad. So I thought I could use my skills, which normally I use a telescope to look up in the sky, but actually to use satellites that can look up down at Earth to try and figure out ways that we can track that plant from the sky, and basically it enables us to do much wider scale sort of sensing for these plants. So it's quite a nice project in parallel to what I'm working on. Now, if we step back a bit and look further out in space, because I guess most of you are mostly interested in astronomy here, or at least that's your common interest. The talk is about black holes, and I thought I should first basically look a bit over, the sort of invention of black holes, give you a little bit of an historical account, and then describe what they are in details, and then see what we know of them and what we've observed. So black holes, obviously, I mean, they've always sort of existed, but we invented them in inverted commas. Basically went with Newton. So Newton in the late 17th century published this book, Principia, and I would probably argue it's probably the most important book in physics ever. If you had to pick one and go on a desert island or something, that's probably the one you should pick. And that's because this book basically describes everything about gravity, but also it contains an immense amount of knowledge about optics and many other fields of physics and even mathematics as well. So Newton, as the legend goes, was sitting and looked at an apple falling off a tree, and figured that perhaps the apple was falling onto the ground for the same reason that the moon is orbiting around Earth. So it was the same force that causes them to be attracted by Earth. And so this was the sort of like germination of the concept of gravity. Now, Newton formalized it with equations, and the sort of primary principle of gravity is that basically objects of different masses, they attract each other. And the more massive an object is, right? So the more mass it contains, the more attraction it will exert on another object. And so what's important to keep in mind is that it's the mass of the object, right? So you can have an object that has, or two objects, right? 1 kilogram of, feathers and 1 kilogram of lead, right? And both of them would have the same gravitational attraction power, right? The same force. So it does not depend on, the size of the object, but really what we tend to call weight, except, in physical terms, it's what should be described as the mass. Now, Newton laid the equations, but he never really talked or described black holes properly. So perhaps he did think about them, but he never really expressed it in a way that we could record. So it's only about 100 years later. So a person called Mitchell describe what people agree is probably the earliest reference to something that is basically a black hole. Mitchell, by the way, was a reverend, so he was a clergyman, and so back in the days, it was very common for clergy people to be, they were well educated and they knew quite a lot about science. So a lot of them were also, they were natural philosophers, as we tend to call, and they knew a lot about, maths and physics, and on top of like everything religion related. So, so Mitchell's idea, right, is the following. His idea was that if you take something, and by then, it had been 100 years since Newton, so people knew that if you take a cannonball or an apple and you toss it in the air, eventually it falls back onto the ground, and we can calculate trajectories of of these cannonballs or projectile if you throw them. So it's described by Newton's physics, and his idea was the following: if you take an object and you make it a certain size, a certain mass, and you sit on the surface, if you throw it at a fast enough velocity, so if you throw it fast enough, it will go further up in the sky before falling back down. But you can actually find a speed at which you can launch objects so that they will fly into space, and basically they would slow down, but it would take an infinite amount of distance for them to slow down entirely and then fall back onto the Earth, right? So at which point the object would basically be free to leave the gravity or the attraction of Earth. And so this is what we call the escape velocity, okay? And the escape velocity, I won't bother you with much maths tonight, so don't be afraid if it's not your thing. Don't be scared. But basically, the escape velocity is basically given by this equation. So it's basically some constant that we call the gravitational constant. But what's important is that it depends on the mass. It depends on the square root of the mass of the object, and also it depends on the inverse of the size of that object, the square root of the size of this object. So basically, if you consider the Earth, for instance, if you want to send something into space, right, and travel to like Mars or anywhere, the object has to reach a speed of something like 11 kilometers per second. If it doesn't go as fast as that, the object will inevitably fall back onto the ground. So when we launch satellites or space shuttles, they go actually just a little slower than that because they stay within the, captured within the gravity of Earth. But if you then, give them an extra push, then they can escape and go to the stars. So it's something like 11-ish kilometers per second. Now, if you take an object like Jupiter is well, give or take something like what is it in terms of mass? I keep forgetting, but something like maybe 50 or 100 odd times the mass of the Earth. I keep forgetting the exact number, but so it would be the velocity you need to escape to escape the surface of Jupiter. We know Jupiter is made of gas, but if you sort of like, go at where the top clouds are, then you would need to go maybe something like 10 times faster. If you go at the surface of the sun, then the sun is even more massive. It's also bigger, but basically you can plug in the numbers, and then you will realize that at the surface of the sun, you would need to reach a few hundred kilometers an hour in order to escape, kilometers per second rather, in order to escape the surface. So now you probably see where I'm going. If you take an object and you make it more and more massive, or if you make it smaller and smaller, then this velocity to escape it would become larger and larger. And eventually you would reach a point where it would require you to go faster or equal to the speed of light if you were standing on the surface of that object in order to, go into space and leave the surface of this object. So if that were the case, you can imagine light, right? The little particles of light on the surface trying to escape and maybe, you know, make it like a little, you know, a meter up or something, and then falling back on the surface. So that's basically the idea of a black hole. Basically an object from which the gravity is so large that if you were to stand on the surface, you would have to go at least at the speed of light or faster in order to escape this object. Okay, so even light would not escape. And that's pretty much what I tend to use as the, you know, the sort of layperson description of a black hole. It's basically just an object that has such a large gravity. So because it's either very massive or compact or both or a combination of both, so that light cannot escape. Now the story goes on because we know a lot more about black holes these days. It took, well, basically a couple more years, and in fact until 1915, for us to have a proper theory that describes, you know, the more like modern black holes. And well, you could perhaps have guessed if we had made a pub quiz about it. So Einstein was the one who actually, you know, sort of like solved it. Einstein basically came up with a better version of the laws of gravity. So Newton's gravity can explain how bullets and cannonballs and typical planets orbit around the sun. But when you look in very detail, like the motion, actually it's not completely accurate. And it tends to be less accurate when you describe, say, the motion of objects that travel very, very fast, or if you're talking about large amount of gravity. So a star, you know, is quite a lot more massive than a planet. So then things orbiting around a star start, becoming a bit different than the typical motion that we would calculate with the equations from Newton. And then if you were to go near a black hole, because the gravity is so much bigger, then you can imagine that the Newton's law, it doesn't work very well. So we need Einstein to be able to explain that. Now, I won't be, given a lecture about relativity tonight, so we won't bother too much about all the details of it. But basically, what's important to know is that Einstein came up with a better explanation of how gravity works. And the one caveat, though, is that Einstein published his equations, but they're just equations, and it basically takes some context to apply them and also figure out what it fully means. And basically, it took 1 year for a German scientist called Karl Schwarzschild to be the first one to solve Einstein's equations for a specific case. And the specific case, it turns out, is the case that applies to basically a black hole. But also it would apply to the case in specifically is basically it could explain how gravity works around an object like the Earth or the Moon or the Sun, which is basically spherical and does not rotate very fast. So the Sun or the Earth, the Moon, they don't spin very fast, and they're pretty much like perfect spheres, more or less. So Schwarzschild could actually took Einstein's equations and worked out how to explain the motion of these objects and everything. It's interesting to note actually that Schwarzschild had been either conscripted or enrolled in the German army. So this was the First World War, and he was actually on the Eastern Front, battling against the Russians when he worked on his physics and mathematical theory based on Einstein's equation. So between his time in the trenches and when he had like a bit of a respite, he would actually pull out the pen and paper and work on these like very complex equations. And so it's really amazing to think someone on the battlefront had like the sort of energy or whatever to work on like really complex physics theories, let alone trying to survive. And it turns out that Schwarzschild contracted an autoimmune disease whilst he was on the front. and he died shortly after coming up with like the solution to Einstein's equation. So it's really sad, because he was one of the brightest physicists in the world at the time, and he could probably have, you know, given us many other really interesting advances in physics. Then something that's also relevant is 1926. Arthur Eddington, so the very famous British scientist from Cambridge, realized essentially the same thing that Mitchell had realized something like 150 years earlier, which is that if you take a star, a giant star. So by then we knew much better what stars really are. Eddington knew that stars are, you know, big spheres of gas, and that they somehow produce a lot of energy. Fusion was not, people didn't really understand nuclear reactions back then, but we were just about. And so he speculated that maybe a star could be so dense, you know, a star like the sun could be so dense that it could trap light. And so this was basically not the same as Mitchell's idea. And then from there on, people then started looking at Einstein's equations, and then they explain what the black holes are. And I'll get in a bit more details of what the modern version of black holes really are. But then perhaps three more landmarks. One is 58. Finkelstein is the physicists who really fully describe black holes as we understand them now. I mean, we know better even now, but that was the first person to really describe it mathematically. And then a couple years later, Kerr came up with an explanation for rotating black holes, which are quite different than non-rotating black holes, or black holes that don't rotate very fast. And then it took until 1964, for the term black hole to be invented or coined. So it was a journalist. So as often, right, journalists, they like to find a good headline, you know, when they report on whatever, including science, and find something catchy. And so that person, Ewing, basically came up with the idea of black hole when they wanted to explain. They had been running an interview with a physicist about black holes, and then they were trying to find a way to explain it to people. So they talked about this thing called black hole. Yeah, so that's like the main landmarks in sort of like our kind of like journey to discover black holes. So now I'll get into a bit more details of what they are. I think you know by now, like, okay, it's something so massive and dense that it traps light, but we can look into a few more details. So as I said earlier, gravity causes the mutual attraction of matter. So if you have like the moon and Earth, they attract each other. So what is, you know, how big would a black hole be, right, given a certain mass? So in principle, like any object, anything could turn into a black hole. But what you need to do is to shrink the object, right, so that it's small enough to trap light when you're at the surface of that object. So, how big or small are they exactly? Well, the speed of light is basically, you know, the key limit, right, for things to not be able to escape. So the radius of a black hole is basically in kilometers, okay, for any object, is 3 times the mass of the object divided by the mass of the sun. Okay, so that's the sort of like key reference. So the sun, right, is 1 times the mass of the sun. So if the sun was to turn into a black hole, you would need to shrink it down to 3 kilometers in radius. Okay. If you were to take an object that is like, I don't know, 10 times, right, a star 10 times bigger than the sun, if you want to work out how big such a star would need to be to turn into a black hole, it would need to be 30 kilometers. And so using this, then you can work out, you know, what is the mass of, I don't know, Jupiter compared to the mass of the sun, and then you can work out how big it would be. So let's look at a few examples. The sun, 3 kilometers, I just said. The Earth, right? So the fraction of the mass of the sun that the Earth is means that if you scale that 3 kilometers, you would end up with a radius for a black hole that would have the same mass as the Earth, would be only 9 millimeters. Right? So imagine shrinking the entire Earth, right, on the size of something that's like not much bigger than a dice. Okay? So you can imagine it's not easy to turn something into a black hole. So you cannot just, wish that it will shrink like that. So typically, black holes, they're born from stars that explode, and the core of the star does not explode, but rather it implodes through like some sort of bouncing phenomenon, and then the core would really shrink down like to a really, really tiny size. So that's sort of how the black holes are formed. And this sort of explosion, that's what we call a supernova explosion. But it only happens for stars that are much bigger than the sun. So an object like the sun will not turn into a black hole at the end of its life. Last example, if you take Lake Windermere, for instance, one of the largest lakes, so in Great Britain, and it's pretty deep as well. If you were to take the entire body of water of Lake Windermere, you would have to shrink it to the size of a proton. So that's protons are what make the nucleus of atoms, right? So they're the building blocks of atoms. So it's really, really tiny. So tiny black holes, like as we call micro black holes, they might exist, but they would be extremely small if they did exist. So what if the sun was to turn into a black hole, right? That might be one of the next questions that you might have. It's one that I get very often. So imagine we take the sun, right? And magically, with my big muscles, I shrink it down to 3 kilometers in radius, right? So instead of being something like 700,000 kilometers, you shrink it down to 3 kilometers. And there you go, you have a black hole. Well, you can't see it, but it's there. It's right there, the black hole. And often, right, we talk about black hole because we talk about a hole, but it's a hole in space-time. So it's not quite easy to visualize what's going on. The sort of best example to describe space-time is basically to represent the dimensions, right, of space, just like the surface of a trampoline, right? So with the surface of a fabric that is stretchy, and then if you put something heavy on it, right, it will create a little curve into it. And the heavier the object, right, the more massive the object, the bigger the curve or the sort of little hole that you will make in that fabric. So this idea of like the hole, right, the curve that you're making, it's not actually a curve that is, properly speaking, like in space, but rather it's a curve that is made in the time dimension. So that's why, because we live in 3 physical dimensions, right, 3 spatial dimensions, like back and forth and sideways and up and down, then the time dimension is like an extra dimension, a 4th dimension. But our brain is not capable of imagining how a 4-dimensional universe is. So what we do with this trampoline example is that we basically imagine a fake universe where there would be only 2 spatial dimensions, which is the sort of back and forth and the sideways on that trampoline surface. But the up and down is not a real spatial dimension. So the up and down then becomes the time dimension in that example, in that analogy. So what happens is if you have something traveling in space, anything traveling in space is basically just like taking a little marble and tossing it on such a trampoline. So if the trampoline is dead flat, the little marble will travel in a straight line. On the other hand, if you put, a big bowling ball in the middle and you toss the little marble, if it travels very far from the center, then the trampoline might be mostly flat, so it would travel in a straight line. But if you toss it like in a direction that's closer to the big bowling ball, then the marble would travel and curve. So depending how far and how fast you throw it, maybe it will just travel and end up on the other side, but it will have changed direction a little bit. And that's what we would describe as a parabolic or an hyperbolic trajectory. So just like comets that orbit the sun. But if you don't toss it fast enough, the marble will basically describe a circle or some kind of ellipse, as we call, some kind of oval shaped motion around the center. And then if there's no friction, it would just keep going around and around. And that's basically the orbit of planets around the sun, right? So they're basically just motion of objects right around, on this sort of curved space-time. So the idea of the black hole, according to Einstein, is basically that you have a hole that is so deep that if you throw things near it, they fall into that sort of like space-time hole, but they're not able to get out of it, right? So because in order to get out of the hole, you need to toss the objects fast enough that they can climb up, to the side and then carry on. But with a black hole, they basically are trapped down. So now, well, usually when I'm in person and I can hear people and everything all talking at once, then I sort of ask people, what do you think happens if the sun turns into a black hole? So instead, I'll go with sort of show of hands, if that's all right. So who says that if the sun was to be turned into a black hole, like immediately, just like that, by the click of fingers, who says that nothing would happen? Or so thumbs up, let's say, and thumbs down, who says that basically, I don't know, something really strange would happen and maybe we would get sucked into the sun, or we would, disappear somewhere in space and away from the sun. So thumbs down. So by show of hands, okay, some people think something pretty bad would happen. Some people, it's about half and half, it seems, and some people are not sure, or some people say maybe both answers, perhaps. So the answer is actually, is actually perhaps busting one of the myths that people, that sort of keeps carrying on in astronomy or in people's mind, is that basically if the sun was to turn into a black hole, basically more or less nothing would change. So we would still orbit around the sun, the black hole sun, and nothing would be different in terms of us, in terms of gravity. So that we would feel the same attraction from the sun if it was a black hole as we feel now. So like I said, the size of the object itself for the force of gravity is not affected by the size of the object. So we would still orbit around the sun 365 days and a quarter. Nothing would change. However, I must admit that the sun is rather important because it does produce an awful amount of light and heat, right? So if the sun was to turn into a black hole, obviously we would no longer get the light from the sun and the heat as well. So things will become, eventually very cold and very dark. Okay, so it would be like nighttime, and then things would get very cold. So it would be a bit like the, that sort of movie where everything turns into ice, and then they're on that train in perpetual motion trying to survive. So eventually, probably, plants, would all die. Everything would turn into a global winter, and then probably we would die as well, who knows. So unless we had we lived kind of underground or whatever. So okay, so in terms of actual humans, might not be so nice, but in terms of physicists, basically nothing would happen. Okay, so so people have this concept that black holes suck everything, but it's not true. The thing that is basically true is that if you go onto the black hole, you cannot escape. right? So black holes are like a one-way system. You know, if you go on the surface of the sun, well, I don't recommend, but except for, you know, melting away, you could, in theory, right, escape the surface of the sun. Light does escape, energy and even particles escape the surface of the sun, but the black hole, you could not. Okay, so that's one myth that I hopefully, you know, for the rest of your life, you know, you won't be tricked by. And actually, the reason for that is due to the fact that the gravitational force, right, how much an object attracts another one, only depends on the mass of that object. And then the rest is just the acceleration. So it only depends on the mass of the object, like I said earlier. And now I've got a little video for you actually to watch. It's a video, it's a BBC documentary. So many of you perhaps watch, you know, my colleague from the University of Manchester, Brian Cox. It might be some of you, you know, one of your favorites. So there was this documentary with Brian where he talked about, I think it was for Galileo's discovery of the universal law of free fall, as we call, and it's not for no reason we call it the universal law of free fall, and you'll see why. But can you hear the sound? Right. So what you've just witnessed, and now I'm.
Now, in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance.
Yep, so I'll just mute Brian. So I'll just play it again for all of you, right? So there's a feather and a bowling ball, and then the little clamps, you know, release and they fall, and then the bowling ball falls much, you know, faster than the feathers. If I had asked like all of you, if you thought, you know, which one would arrive first, I would imagine you would have said the bowling ball, isn't it? So, and that's because of the air resistance. But now what Brian did is, you know, I don't quite have that budget, but when you're Brian, I guess you can. He went to this place in California, so that's where it was recorded. A giant, like the place where he is a giant cylinder made of concrete and whatnot. And they can actually close it and then create a vacuum. So they can suck out all of the air from the vicinity and from the container, and then they can experiment. And it's used for, well, all kinds of physical tests. But for instance, when they want to test hardware like computers and parts of that go on satellites and spaceships, for instance, because there's no air in space, then they can put things in there and check out, you know, if everything would work properly. So now they did this experiment where they did again the same free fall test with the feather and the bowling ball, except that this time around they took away all of the oxygen, well, not oxygen, even like air or whatsoever from the room. So who says that the two will fall at the same time, or the bowling ball will fall faster, or the feather will fall faster? So cast your vote. Okay, some say they will fall equal. Some say bowling ball will fall faster. I don't think anyone says the feather will fall faster. No. Okay, so it's between the same or the bowling ball still faster. So let's see it.
5, 4, cameras on, 2, 1, release.
And then it's in slow motion. We can see it very well.
Exactly. Exactly. They came down exactly the same. Wow.
Look.
That's right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant.
So there you go. I find it amazing. This is potentially my favorite ever physics experiment, because I've done it when I was little, and also I do it in like with school groups sometimes when I visit. You know, I sort of climb when I can on the rooftop of the school, whatever, and I drop a pumpkin or whatever, and there's, you know, a smaller object, and try to show that it falls at the same rate. But obviously, it never quite works perfectly. And allegedly, that's what Galileo did from the Pisa Tower. But with technology these days, you know, we can remove air, so then there's no friction, and it does work. And also the video is just very funny, because, you know, you have the controller, and even though, just a bit like you probably, even though some of you know what should happen, when you actually watch it and it does happen, it's mesmerizing, because it's not something we tend to see. By the way, if you're good on YouTube, you can also search for the Apollo 17 hammer and feather experiment. Yeah, someone just posted just as I was saying. Thank you, Peter. Yeah, so the astronauts on Apollo 17, they basically had like a hammer and then a feather, an eagle feather, and then they dropped it. And it does work on the moon's surface as well, because there's no air. It is very amazing, and actually it was probably the most amazing potentially until the video I just showed. But the sad thing is that it doesn't fall from very far up, right? It's only like a meter drop, so it kind of maybe looks a bit less impressive. I don't know. Okay, so the gravitational force only depends on the mass of the object. The rest is just the gravitational acceleration, which is basically a constant. So that sort of hammers the point that I was making before. The sun, if it's a black hole, or if it's a sun size, or if the sun was the size of the Earth, it doesn't matter how much gravity it produces. It only depends on the mass of the object. Well, actually, I should put a small asterisk, because that's according to Newton and according to Einstein, Einstein's theory being the best one we have so far. But there are other theories where they don't predict that this would necessarily be the case, and I'll get back to it a bit at the end if I can. Okay, so now let's do this sort of virtual experiment. Anyway, we're all on Zoom, so everything's kind of virtual to some extent. Let's try and imagine what would happen if we fall into a black hole. And that's actually a good way for us to see a bit what black holes are in the more modern sense. So imagine that we have two persons, and both of them are kind of hanging out far from a very mighty black hole somewhere, and one of them is a bit of a fool and decides to dare to the other one that they're just gonna jump, feet first perhaps, because head first might be a bit too scary. So jump into a black hole and see what happens. And the two of them are a bit, they're really obsessed with time, like Einstein was, right? Because time and is really important in physics. So they both carry a stopwatch or a clock, and they both synchronize them at exactly the same time, just for fun. So now one person goes on. Oh, sorry. Apparently it was the Apollo 15, not Apollo 17. I thought it was Apollo 17. Anyway, we can check facts later. Yeah. So okay. So the one person goes towards the black hole, and then the first thing they would start noticing is basically that time would appear differently from the two persons. So so the person that stayed away, right, would look at their clock and would see, let's say, a couple of, let's say a full day has gone by. But then the person that goes closer to the black hole would look at their clock, and they could see maybe only an hour have lapsed since they had left. So the person that's far away who looks at the clock, or the person that's there and sends some kind of a signal to tell them what time they have, right? And they sort of compare the time. they would realize that the person that's closer to the black hole, for them, time actually seems to go more slowly. But the thing that's also important to realize is that it's just a perception effect. So it would be, so that time would look slower for the person, you know, that's far away, who looks at the person going near the black hole. But the person who goes near the black hole, things would look kind of normal. So an hour would be like an hour, right? So it's not like everything all of a sudden would, you know, if that person was to talk, it's not like they would talk in slow motion and like they would move in like slow motion. It's only for the person that's far away, they would see them kind of like moving slowly and talking slowly. But the person locally, time would feel the same way. But it's just a matter of perception. And this is a bit what Einstein means when, you know, with the name of his theory, the theory of relativity. Because it's all how things are perceived with respect to one another, right? Whereas locally things can look very much the same. Okay, but in real life, right, it would elapse, you know, at a more at a slower rate. So if the person goes near the black hole and spends some time there and then come back, then the person would actually be younger than the other person when they come back, because time for them has been ticking more slowly. Okay, so if you're, you know, I've just turned 40 this year, and I can't, you know, I'm kind of getting to the stage of wanting to be a bit, you know, younger. So yeah, I could potentially go on holidays near a black hole, you know, every so often and come back and look so young compared to those who don't go on holidays. But I think going on holidays always makes anyone look younger anyway, so it doesn't have to be near a black hole. Okay, so what happens next? Well, they keep going, and then, yeah, they decide to go feet first. It's a bit less scary that way. When they reach a distance from the black hole, which is, we call it the radius ISCO, and ISCO is just an acronym, so it means the innermost stable circular orbit. So it's a technical term, but basically when you reach a distance from the black hole, which is 3 times the size of the black hole. So that's what it means here. I just put it in sort of numbers instead of putting in full words. But basically, when you're at 3 times the radius of the black hole above it, then you're at the point where if you're on a spaceship and you want to, you know, orbit around the black hole, this is your last chance to be on an orbit that is a circle around the black hole. If you go any closer, you don't have a choice, but your orbit will have to be what we call an ellipse. So an elongated orbit, which is such that sometimes you'll be inside that radius, you'll be closer to the black hole, and then you'll have to kind of like go outside at some point in the orbit and then come inside and outside. But at that point, it's the last place basically when you can have like a nice stable orbit. Inside of that, then orbits start becoming unstable, and then things are more tricky. So it's basically danger zone, right? You're kind of like in the red zone when you get in, you know, in there. Then you carry on, and then you get closer and closer to the black hole. Then at some point you will notice that the tidal distortion becomes very extreme. So you're aware of tides, I can imagine. I believe most of you are located somewhere, like northish of Sheffield. Is that the case? Somewhere Yorkshire? Yeah.
It's just a little bit north of Sheffield, just about 5 miles.
So a bit like me, you're not quite by the coast, but hopefully you've all seen tides before, right? So the tides are created by the gravitational pull of the moon primarily, also a bit the sun, but the major effect is the moon. So the moon, despite the fact that it's only about 1/6 of the mass of the sun, it pulls quite hard on Earth. And rock, for instance, everything that's hard and solid, you know, is as it is, it doesn't move. But water, because it's liquid, can actually be pulled by the moon. So if you were to look at the shape of Earth, the oceans basically make a bulge in the direction of the moon and opposite to the direction of the moon. So it's like the earth is a bit squashed. And so we rotate, the earth rotates. So this means that like the position in line with the moon, where the earth is a bit bulgy, will change as a function of time in the day. So, and that's the tides for you, basically. So every time we point towards the moon or away from the moon, you have a high tide, and then in between you have a low tide. The full thing is a bit more complicated. The sun also has an influence and everything, but to first approximation, that's pretty much what happens. If you take even a solid object, right, and you bring it close to a much more massive body than the Earth, like Jupiter or Saturn, you can actually take a small object and make it fly into pieces, and that we believe that's what creates the nice rings around Saturn. That basically was some kind of a moon that got too close, and then the moon, fell into apart because of the gravity. So you can imagine now, if you were to approach a black hole and get really, really close to it, right? Gravity can become insanely large to the point where you would experience the spaghettification effect. Okay, and that's a real physics term. So when you read like even serious physics textbooks, they do talk about the spaghettification effect. And basically, everything is basically turned into noodles, because the effect of gravity, and that's the effect of tides, right? So if you have someone that goes feet first, their feet are closer to the source of gravity, like the black hole, than their head is, right? If you go feet first. And so your feet are more attracted than your head. And so the feet are pulled more, like in a relative sense, your feet are pulled more than your head, and therefore it tends to elongate the objects. And that's why the Earth is elongated. Like, people often wonder, why is the Earth bulgy in the direction of the moon, but also opposite the direction of the moon? Why isn't it not bulgy only in the direction of the moon? Because that's where the moon is, not opposite to it. And the reason is that it's because the side that's facing the moon is more attracted by the moon than the other side. And so it basically elongates the object. Okay, so if you or anything gets closer and closer to a black hole, they will become elongated. If it's a human or a spaceship or a satellite or a moon or even a star, you can imagine it might not be too fun at some point, because basically it would be turned into spaghettis. So we'll just imagine that we have a very stretchy person doing the experiment for us, because otherwise, yeah, that would not be, there might not be one person, it might be several pieces of someone. But we'll just imagine that that person is really stretchy. So eventually they become very elongated, and then they keep going and going, and then they reach, right? And don't look at the feet, but look at the middle of the person. They reach a point where they're about half of the size of the black hole above the surface. So basically from the center, they are located at 1.5 times the size of the black hole. At this point, we reach a special position in space that we call the Photon Sphere. And what this Photon Sphere is basically the point where, if you have even light, which is what travels fastest in our universe, nothing can go faster than light. If you have light, it will be at a point where light could only go tangentially to the surface up to that point. If you go right inside, a bit closer to the black hole, and light, you try to, shine light parallel to the surface of the black hole, light would basically fall onto the black hole. Just a bit like, you throw something and it kind of like falls onto the ground. If you are right at that point, light would be just about capable of going around without falling onto the surface. So from that point onward, if you go further in, the only way for light to escape is to be emitted in a way that kind of looks outward, if that makes sense. Okay, is that clear what I'm trying to explain?
Yes, thank you.
So the main consequence from that, the one we really care about, is that the person there, right? They could see their rear bottom, right? Because when they reach that point, the light, if they had a flashlight on their back or something, the light that's emitted from their back would be able to travel like some kind of a full orbit and come back right to their eyes. Okay, so I know a lot of us would not, really probably enjoy seeing what we look from behind, but that would be, your last chance. Then if you keep going, then light has to be emitted outward to escape. And then you reach the point where you hit the black hole surface. Okay, and at that point, basically what we call the cone of light, right? The light, some of the light that's emitted too much, tangentially or downward or even upward, would not even escape and will fall back onto the surface. So it sort of makes a cone of light that can escape. When you reach the surface, the only light that can escape would be, just before you touch the surface, would be light that goes exactly away from the surface. And when you reach the surface, this sort of cone of light wraps up, and then no more light can escape. Okay. At that point, you're on the black hole surface. Now, bang, you hit the surface. Well, actually, you don't, because black holes don't have an actual physical surface, like a hard surface. So there's this really weird thing, and that's what basically was a consequence from Einstein's relativity theory, is that when you reach the surface, actually all the matter that's there has, by the laws of Einstein's relativity, all the matter needs to keep going forward because of what we call the flow of time going forward. So everything has to keep going towards the middle until they reach the very center. So an actual black hole, as we understand it in the modern way, all the matter that forms the black hole and everything that the black hole absorbs ends up right at the very center of the black hole. In between what we call the surface of the black hole, in the physicist sense, we call it the horizon, because an horizon is not something that's hard, it's just like a point of view. So from that horizon, you cannot see further. And so that's what we call the surface of the black hole, the horizon, because the person that's outside of the black hole, when they look, they cannot look past the horizon. Okay, so it's really strange, because all matter, it doesn't depend how big the black hole is. It could be a 1 gram black hole, or it could be a black hole, of 3,000 or 3 million times the mass of the sun. All of it is in the very center at what we call the singularity. The other thing that happens is that time would appear to basically freeze as you reach the surface, as seen from someone that is outside. If somehow you were able to survive it, then time would keep ticking for you. But the person who looks at you from outside the black hole, they would see everything freezing in time just as you cross the surface. And it's related to this concept of redshift. So the second thing that's kind of interesting actually is that black holes are black because light cannot escape, but actually, practically speaking, it's not really the case. They're black because stuff that's on the surface gets infinitely redshifted when it tries to escape. So basically, light that is blue becomes redder and more red, and eventually the light turns into microwave light and radio light, and eventually it becomes into such such low frequency light that it's not even detectable and nothing is emitted. Yeah. So okay. So now I know I've been talking for a little while, so I'm going to conclude in a few minutes. But I just want to show you some sort of real-life example of black holes. So because all of it was basically a bit theoretical so far, but actually black holes do exist. We do have observational evidence of it. So for instance, if you look in the constellation of Cygnus, right, Cygni, which is visible in the typical summer sky, you look in this, this is I believe, Deneb from the Cygnus constellation. And not far from it, or it might be at the head of Cygnus rather than Deneb. I've forgotten. But if you look right there, and then you were able to zoom in, obviously that's not what you see. This is just a cartoon image. But we detected a very bright star. It's a star that's about something like 18 times the mass of our sun. So it's a big white bright star. And that star, we can measure its motion, and we see that it orbits something else. But what it orbits, we cannot see. It's basically not emitting light. So it could be a very small other type of object, like a white dwarf or neutron star that we could not, see because it's too faint. But actually, from the motion of the orbit, right, using even just Newton's laws, we can actually tell how fast, and how long it takes and what the distance from the other object is. And actually, we can calculate that the mass of the other object is something like 11 times the mass of the sun, but it's very tiny. And we know that objects like white dwarfs or pulsars or neutron stars, other types of compact objects, they cannot exist at such large mass. So it has to be a black hole. So this is a black hole, what we call a stellar black hole binary. So it's got a 5.6-day orbit. And there are many of them. We know hundreds of them in the sky, in our own galaxy. Now, this is the Milky Way. So if you stargaze sometimes, maybe not right too close from a city, but, and also, I know in this country, sadly, we often have, non-clear sky and rain, but if somehow, on the one day a year that is clear, you can probably see the Milky Way, and the center of the Milky Way is basically in the constellation of Sagittarius. And if you zoom in where we think the center of the Milky Way is located, and now that's what the little video here shows, you can actually see, I'll just freeze it there. So that's an optical image, basically showing near the center of the Milky Way. It's full of dark spots because that's like very rich in dust and gas, and they tend to absorb light a lot. So for those who stargaze, you might or might not know that if there was a star right at the center of the Milky Way emitting light to us, the absorption of light, because of all the junk that's in between, would make the star look 30 magnitudes, so 30 magnitudes fainter than it would actually be if there was no dust along the way. Okay, so even very bright supergiant stars near the center of the Milky Way are difficult to observe because we do have telescopes that are powerful enough to see them that far, but they are very absorbed. So typically, what we do is we switch to other wavelengths. We switch to telescopes that can observe in the infrared, because infrared can actually see through these clouds of dust and see stars that are, essentially hidden from optical light. And so now we switch to images taken by telescopes such as the VLT in Chile or the Keck telescope in Hawaii, and they are able to observe the near infrared. And this image that you see now is taken in the near infrared. Now, near the center of the image is where we think the center of our galaxy lies. And pay attention to the star. So it's a little blob right in the center of this circle. So this is an image from 2004. And now you'll see a time lapse of multiple images that were taken. Now we just enhance the contrast a little bit. And you can see what happens to these objects. Right, so all of them are moving a little bit, and this one is like jiggled around, right? And if you go back in time, then you can see, ooh, it sort of kind of makes a little projected kind of not a perfect circle, but you can imagine maybe a circle seen from the side, so it looks like a little elongated trajectory. So this is the motion that was measured by these telescopes. So here is basically a chart that basically notes the position of every star we could localize near the center of our galaxy. And what we called SGR A star, so Sagittarius, after the constellation, A star is what we believe is basically the center of our galaxy. The size is 0.5 arcsecond. This is the size of this line here. So the moon is about 30 arc minutes in size, right, in the sky, like that's the angular size. And 1 arc minute is made of 60 arc seconds, right? So this line is something like half of a 60th, so 1/120th of 1/30th of the moon, right? So it's something like 1/500th of so the size of the full moon in size. Okay, so it's really, really tiny. You need to zoom in a lot. Now, what people did is they took the positions at different times and then they plotted them on this animated chart. And what they've been able to do is basically to measure the motion of these stars in the very center of the galaxy, where gravity is strongest and where the stars orbit, with the shortest orbital periods. And basically the smallest orbit is something like a decade. So it's research that's been going on for almost like 30 years now. So we've seen like over like 1 or 2 orbits so far. And this research actually incidentally was awarded the Nobel Prize of Physics, I believe, this year. So so there was Andrea Getz and I forgot what the other person are, but they were awarded the Nobel Prize for Physics, or maybe it was a year ago rather, because this year was Penrose, wasn't it? So yeah, time flies. But basically a year ago, Nobel Prize of Physics for their research. So using the motion that's there, we can actually tell how big the central object is, okay? And we basically discovered that it's a black hole which is 4 million times more massive than the sun, okay? So take 4 million suns and you cram them. And why we know it's a black hole is because this entire mass fits within the orbit of the object, right? The star that orbits the nearest, the object, can orbit around. So the central object has to be smaller than that. And basically the orbit of the star that goes nearest to the black hole is an orbit that is something like the size of our solar system, like the furthest planets in the solar system, like Neptune or something thereabout. Okay, so you basically need to fit something like 4 million sun within the size of the solar system up to Neptune or Pluton, okay? And essentially only a black hole can be so compact. However, there's something I'd like to tell you, which is the fact that black holes don't all have the same average density. So I said earlier, all the mass is in the central point in the black hole, like infinitely small. But if you consider the black hole as some kind of a physical entity, right, that reaches the horizon, right, at that point light cannot escape. So if you consider that region of space and you were to calculate, basically what is the total mass of the black hole and you divide by the volume of that region, what you would find actually is that the density, right, that's the definition of density, the mass divided by the volume. You would find actually that the black holes, they become less and less dense as the mass of the black hole grows. So if you double the mass of a black hole, the volume of space that they occupy compared to their mass is actually much larger. Okay, so black holes, they kind of grow, so mass divided by volume. So sorry, their volume rather doesn't grow as fast as their mass grows, I should say. So what this means is basically if you have to choose to be sent near a small black hole or near a big black hole, you probably want to go near a big black hole because you can reach closer to the surface with less spaghettification effects. That's what it means. So at the surface, you will feel less, pull than if you're near a big black hole. These big black holes, we know they exist. So that's a nice picture, optical image in sort of orange. But then there's like these big jets here, which are which are radio images that are added to the optical image. And the sort of glow that you see is X-ray. So there's 3 types of light that is put together. So this galaxy, if you look with an optical telescope, it's basically some kind of a blob, a rounded blob. But then when you look with a radio telescope or an X-ray telescope, you see these massive jets that are produced above the plane of that galaxy. And what we think is happening is that there's a supermassive black hole, a bit like the one at the center of our galaxy, but this one is very active. It's basically absorbing a lot of stars and gas and material that comes too close, comes inside the hole, and then doesn't escape. But as the matter falls onto it, the matter heats up, right? Because it becomes spaghettified and it releases gravitational energy. And some of the matter actually, before it falls onto the black hole, some of the matter gets pushed away and it gets accelerated along very fine jets along the poles of the black hole. So that might be what it could look like, if we could go and get closer with some kind of a, Star Trek kind of spaceship. Now, we did observe black holes colliding before. So this was a prediction from Einstein in 1916, actually. He predicted that when objects orbit one another, they create ripples in space-time. And if you take objects and you make them collide, they would produce a huge amount of ripples. A bit like, if you take a rock and you drop it into a bucket of water, right? It creates like some kind of a splash and waves and ripples that propagate. So Einstein predicted that these waves that we call gravitational waves should exist and should in principle be observable. And it's only in just about 100 years later that we were able to observe these waves directly for the first time. So when these waves passes through Earth, it literally creates, it makes the Earth and everything jiggle. So it literally changes space-time. So it changes the physical dimensions. And we can try and detect those using very accurate lasers in an experiment that's called LIGO. So you shine lasers in directions that are perpendicular. And if one of these waves passes, basically it will kind of like shrink or stretch space-time. So it literally stretch dimensions. And if you measure, like with the laser, the distance between the laser and a mirror that reflects it back in one direction and in a different direction, then if that jiggling takes place, you'll see that the dimensions will change. And so it's been done in 2015. And another Nobel Prize for that discovery. And this was created by 2 black holes, about 30 times the mass of the sun each, that collided in a distant galaxy that's located about 1.4 billion light years away from us. And what you see there is basically the sound is the sonification of the jiggling. So you can imagine the laser measures the distance, right? And essentially the lasers, I'll just turn off the sound, the lasers measure the distance, and you can imagine basically when it measures it, it essentially tries to measure the vibration that's created by these waves passing. So if you take the vibration and you turn it into a sound, that's what it would sound. And the actual vibration is recorded a bit like a seismograph, if you want, to measure earthquakes. So it was measured at 2 different locations, one that's in Louisiana, and the other one is located in the state of Washington. So both in the United States, but about, you know, a few thousand kilometers away from each other. So the vibration that it detected happened at exactly the same time at both places. So if it was something local, like an earthquake, or they can even detect airplanes or tumbleweed, you know, for that matter, that rolls on the ground, because even tumbleweed makes the ground shake and can be detected by these lasers. That's how accurate they are. But the same vibration was detected at the same time at both places. And that vibration corresponds to a change in the size of space of something like 1,000th the width of a proton, which are particles that make up atoms. So that's why, you know, when gravitational waves pass through Earth, which happens probably every day, you don't see everyone jiggling around because it's not perceptible. Okay, the very last thing is we also took pictures of black holes. So this happened a couple years later, so about 2 years ago or so, using what we call the Event Horizon Telescope. So I said earlier with the, you know, the VLT or Keck telescope, we can take very nice pictures of the center of our galaxy and see the stars moving. But to make even sharper images, we can actually use telescopes that are sensitive to radio waves or microwaves, basically. So somewhere in the few hundred gigahertz frequencies. And so the telescopes, they are the ones that you see there. They're located a bit all over the Earth, and they can be linked up together in a way that we call an interferometer to actually to produce a very sharp image. So they looked at a well-known galaxy, M87, so Messier 87. So you might have seen it. It's in the Virgo constellation, and we know that there should be a supermassive black hole in that galaxy. So they looked at it, and they were expecting to see essentially like the black hole, which you don't see directly because it's black, it doesn't emit light. But if there's matter that orbits it and falls into it, before it does so, it becomes really bright and makes a big bright ring around it. So they were looking for that ring, basically. So this is basically the last video, and it basically shows what happened. So looking the Virgo constellation where M87 is located, and then you'll first see an optical image. It looks a bit like the image that I've shown before of the black hole in Centauri A. So there you go. So at the center is like a blob, a bit like the one that sorry, I'll just rewind just a tiny bit. These blobs, like this and this, are what you typically see with optical light. So there is a blob at the center, and that's what you normally see with an optical telescope. Except that here they also added the radio image. And then again, that galaxy, you can see these big jets that come out and indicate that there's a supermassive black hole in the galaxy that's actually absorbing a lot of stars. So you can see that jet. And then if you were able to zoom in, and these are all real images, you can see images made with like very powerful radio telescope. And then using that Event Horizon Telescope, you can see the black hole shadow and the ring of material that's around, that's being produced. And yeah, so we can measure how big this black hole is, 6 billion times the mass of the sun. So it's a supermassive black hole. I'll just skip over that. But just to give you an idea, the amount of data that needed to be collected to make that image, only that image, was 5 petabytes of data. So it's about 5,000 laptop hard drives, or iPhone hard drives, if you want. So it's an insane amount of data. We can measure how the black holes spin even when we reconstruct like the physical parameters for that image. But the size of this little donut-looking object is roughly the size of a grain of rice that would be held by someone located in Melbourne. So if you take the distance, Mexborough to or Yorkshire to Australia, right? accounting for the curvature, which is I don't know how many miles, and then you ask someone to hold a grain of rice. That's basically the size of what we've been able to see on that picture there. Okay, so a magnificent feat of modern physics. Okay, so I'll stop there. Sorry, I took a bit longer for my presentation than I should have. I'm happy to field some questions if people are not too tired.
Rene, don't worry about overrunning, because it was a very interesting and absorbing talk. I don't think anybody really wanted to finish. So what I'm going to do now is just to remove the spotlight from you and to go back to gallery view so I can see people. What we do now is I'm going to ask people if they've got a question to ask by either putting up a hand, raising a digital hand, or by waving at me. So Peter Jarowatsky, can you unmute yourself, please?
Yeah, hi, fantastic lecture, I really enjoyed it. I do have a question. When you were going through your slides, I think when you showed the slide showing the third, the last critical radius from the black hole, which you could have an orbit. What crossed my mind is there's a lot of being said about how you can't extract information from a black hole. Now, if you put that to one side, and if you consider you've had spacecraft going around the moon, and they can detect irregularities in the moon's gravitational field, for example, mascons. Could that be a way of detecting irregularities in the any irregularities in the gravitational field of a black hole, for example? Once techniques get better, for example, that could test whether there is a theory, whether there is a singularity at the center, for example, looking at the movement of the material around the south of the black hole.
Yeah, it's a very nice question. I might sort of reward it a little bit for those who might not have fully understood, because it's a bit of a more advanced concept, I would claim. So basically, there are spacecrafts that either using laser ranging or sensors, they can detect gravity basically, and they can measure the force of gravity, say, whilst they orbit around Earth or around the moon, right? And then we can sort of tell if there's irregularity in the gravitational field. So for instance, if you take the moon is not perfectly homogeneous. There are craters and whatnot, and regions that are a bit denser than other ones. So if it's not perfectly spherical and smooth, you can actually detect it. So that's, I think, the essence of Peter's question, if I understood correctly. Yeah. So now we could potentially send some kind of a probe like that near a black hole and see if it's perfectly nice and spherical. As it turns out, so our best theories of black holes say that black holes are what we call hairless. Okay, black holes have no hair, like maybe some of you or maybe me in a couple of years. So what it means is that if you take I don't know, a star and you dump it onto a big black hole, the black hole, as soon as the star hits the black hole, the black hole would become perfectly uniformly distributed, and there would be no lump or no bump onto its surface. So in principle, according to what we know of, you would detect no change. It would be perfectly, sleek on the surface, if that makes sense. Now, we can actually try and do experiments. So using pulsars, which is one of the types of objects that I'm studying, we can time pulsars. They blink, and they blink in a very regular fashion. So what we hope we can achieve one day is detect a black hole and a pulsar that orbits it, in close proximity, especially a big black hole. So what we'd ideally like is to find, instead of finding one of these stars orbiting the center black hole of our Milky Way, is to find a pulsar that would orbit at a similar distance or even closer. And because we can measure pulsars way better than calculate the velocity of stars, we can actually test this very idea that you're talking about, like what we call the no-hair theorem. So in principle, colleagues of mine that are, theorists, they're working out ways of how we could measure the blinking of pulsars near black holes, in orbit around black holes, to test this very idea. So if we were to find that it didn't match the observations, then we would learn like something completely fundamentally new about physics. So hoping we can do that. If I'm honest, I would probably say timescale for sort of a black hole to be discovered there. Well, it could happen any day, but we have a big radio telescope called the Square Kilometer Array that's kind of started to be constructed, and by 2030 would be fully operational. So we think by the time it's fully operational, we should find these pulsars. So if we give it about 15 years, I think we'll get about to the point where we should be able to kind of do these experiments, hopefully.
Thank you.
Okay, Peter. Thank you for the question. Peter Lloyd had his hand up. Peter, did you have a question?
Yes, thank you, Paul. Well, thank you, Rene, for a most interesting talk. Well, I've got two questions actually, but the one leads a little bit out of what Peter's just been talking about. You said you could, in principle, have a spacecraft that was in an elliptical orbit, part of it being within the orbit of, I forgot what you called it, the last stable circular orbit, and then it would loop out of that. Is that right?
Yeah, it would be something like that. Yeah, basically there's no, mathematically speaking, in terms of dynamics, there's no solution for a perfectly circular orbit, but then elliptical orbits are allowed within.
So that's fine. Now, I wondered whether when that spacecraft was at its closest point to the black hole, would it be able to pick up light that was being transmitted out of the black hole, because it has not yet slowed to zero, and then record that and transmit it out when it got to the outer part of its orbit?
Yeah, sadly no, because well, maybe it's clear, but I'm not sure. But the orbit would go not inside the black hole, right? The orbit would go in and out of that last stable orbit limit for like a circular orbit. So the orbit would be elliptical, but it would not go inside the black hole. It would go closer to the black hole and further, but it would not go inside. And then even if you were to stand like, I don't know, as close as you can, but like 1 millimeter above the black hole, at the moment something crosses that horizon, that virtual, kind of barrier, you just can't see it anymore. Like as soon as you cross it, that's it.
You seem to imply that the reason the light can't get out of the black hole is it starts out, but it gets slower and slower and slower and slower as it goes up, until eventually it stops and falls back in again. Now, what you were calling the surface of the black hole, is that the point where the light finally stops, whatever its initial velocity? Well,
yeah.
Or is it that that's the point from which it will never escape completely, but it will go out a certain distance and come back again?
Yeah. So in fact, so that description is, well, it's a bit of an analogy. So it's, sometimes we can't quite explain, the same way we would with maths, but actually it's also kind of accurate in the sense that at the surface of the black hole, like if you go at the surface at the speed of light, you don't even rise up the surface. You're literally like stuck on the surface, or basically you go down. But if you stand just a bit above the black hole, so that's what I was explaining with my cone of light earlier.
Yeah.
So basically, if you stand a bit above the black hole, right, and then you have light, and you shine light, but not perpendicular to the surface, but at some angle. If you shine it at a bit too sort of like close towards the surface, even if it's outward, light will go up and will come back down, and will kind of orbit around. So it would be a bit like if you have like a ball, right, and you throw it and it goes up and sort of like curves and kind of go back down, except you're in orbit, right? So on Earth, things slow down and everything because of friction. But if you're like in orbit and you kind of like throw something, a bit further, but not fast enough, it will kind of fall back down and then will kind of orbit. So light would do the same. It would be bent around the black hole. But when you when you reach the surface, the horizon, like things don't even sort of go up and down. They literally cannot. There's only one way, and it's forward, inward.
I see. I think yeah. I think
Okay, I've got a question that sort of goes on from that. So we've got this this idea that the radius of the black hole, and then you showed us that equation 3m divided by mo kilometers, and that describes the describes the horizon. Is that correct?
That's correct.
Yeah. Okay. So, but how big is the singularity? Or isn't that a sensible question?
Infinite. Well, yes and no, but actually a lot of like theoretical physicists, that's kind of what they do for a living. But basically the singularity, I mean, as the name perhaps allude to, it's infinitely small, literally as in like it's a single point in space.
So are we talking about
that?
Are we talking about the smallest unit of length, the Planck length, or?
Yeah, so even smaller. It's literally one point in space. And yeah, what I was going to say is that it makes people freak out a bit to think that all mass can end up in like one point in space, which is very, you know, strange and absurd to some extent. But as it turns out, that's what we believe it is, but it's also making physicists, you know, sort of take their human cap on, off rather, and put, you know, the pure physicist, you know, mathematician point of view. And it makes them freak out as well, because when things reach very small sizes, what we call like the Planck scale, or basically, you know, atomic scale, then gravity tends to not work really well, and you need a different theory to explain the motion and the behavior of bodies, and that's what we call the quantum theory. And so whereby things can be in different places at the same time, or you can't quite determine the exact location of an object. So so basically on small scales, when you reach like a tiny scale, you need quantum theory. And then we don't really have a quantum theory that actually works hand in hand with the gravity theory. So that one theory, gravity, like Einstein's theory, can explain the large scale and masses and attraction. Then the quantum theory from people like Schrödinger and Heisenberg can explain the behavior of tiny things, like how atoms behave and whatnot. But the two, they should meet somewhere and kind of like, you know, work together in a super theory, but we haven't found that super theory so far. So that's what people, the unified theory of everything. And, you know, Hawking himself was working on it. Einstein worked on it. No one has really found, you know, the full answer to it. But the thing also is that our physics theories, they don't really work well at very small scales. And beyond that Planck scale, we basically don't know how physics behaves. So people are very baffled because basically we can't quite fully explain, you know, black holes.
Right. Okay. It's back to the beer and peanuts. Catherine's waving at me desperately. So, Catherine, can you unmute yourself?
Yes. Can I ask two questions? The first one is, you mentioned about having that ellipse trajectory, but I thought under general relativity you couldn't get elliptical paths because they wouldn't join back where they started from, and that is why you get the precession of Mercury. And that's the first one. And the second one is postulated that there is a particle called a graviton, which is a spin 2 boson, and it's a very low mass, and it could actually have, and it could be massless. If it's massless, then it would be traveling at the speed of light, but in a black hole, light cannot escape. So if there were gravitons, how could gravitons escape from the black hole?
Yeah. I must say, yeah, there's lots of very, lots of strangeness about black holes. So about like the orbits, you're right. What you said, right? About so in Newton's theory, for instance, you can have something that kind of orbits around and around on exactly the sort of like same paths. Whereas like in Einstein's theory, this does not happen. And this is what gives rise to the precession of Mercury's orbit. So so it's a I didn't really prepare for it, but basically it's basically like taking kind of like making a path on a piece of paper, and then kind of like wrapping the paper to be like, you know, a curved space-time. So something would be orbiting on a flat space here, but then would be on a curved space-time. And then if you look at how the motion in there would be, essentially it doesn't wrap around. And then it has other consequences. So if the black hole rotates, that's why I said earlier, you know, in the landmarks, there was like this thing about black holes rotating and non-rotating. If the black hole rotates, it literally drags space-time around it, which is really mind-boggling. So space-time is actually something a bit like molasses or honey, if you want. So, you know, if you, like when you have like, I don't know, toast in the morning or something, I like to put honey, and, you know, I have one of these honey or, you know, just a regular spoon perhaps, and you dip it in, right? And if you kind of roll it, you can see sort of like things around being dragged. So, so rotating black holes, they do that. They sort of drag space-time around themselves. And so when you send particles, if you send a particle in one way, it might actually orbit, and then eventually its orbit will change direction, and eventually might sort of like spin completely opposite the direction you sent it, and might come back the way it came from. So there's all these weird things going on with black holes. And the thing about gravity is quite strange, though, because gravitons might sort of not have mass. How can they escape and everything? That part, I don't have a full answer to that, except for just the pure fact that basically mass distorts space-time, so it can have like a long-range effect on the space-time. But in terms of a particle theory of space-time, I could not quite explain how that works.
Okay.
Thank you very much.
Thank you, Catherine. And just one last question then from Roy.
Yeah, it's going back to this issue of a rotating black hole. Two things is, what's actually rotating, because it's infinitesimally small, and B, how fast is it rotating?
Yeah, indeed. So if something is infinitely small, how can you tell it rotates, right? Because usually you track the surface. So, but for a black hole, you can't. But I guess the only thing really is, in terms of physical laws, something that rotates, we say it's got an angular momentum, and it's kind of like some quantity that you can measure in different ways. But one way is, for instance, to see the effect on space-time of that rotation. So a black hole that rotates, like I said, it distorts space-time, and that it's basically the indication that it does rotate. So it has so it's a bit like magnetic fields, right? A magnetic field is sort of invisible, but we can tell its presence even though we don't quite see the magnetic field, because you can put something metallic and you see it aligning or being attracted. So a black hole that rotates, you cannot see it rotating, like sort of, so to say, but you can actually tell that it has a rotational quantity. So black holes actually are described only with three quantities. They have a mass, they can have a rotation, and in theory, they could have a magnetic field. But that one is, people don't really believe that black holes have any. So I won't get into the details of why, but we don't really believe that typical black holes will have a magnetic field. How fast they rotate is a really strange question, in the sense that in units of sort of, meters per second or whatever, I cannot really tell you actually. I would need to compute equations, but because we describe the spin of a black hole using that quantity that we call the angular momentum, and we express it in unitless units. So we divide the sort of amount of energy that's in the rotation by the mass of the black hole, and it gives a value that is between 0 and 1, basically. So yeah, so it's not very useful. However, what I'll do is I'll try and work out for, say, a black hole like the sun, let's say, if it was spinning at the maximum theoretical speed, because basically there's a speed beyond which they cannot speed faster. So there's a maximum speed. So I'll try and work out what that maximum speed would be if you were at the surface, if you were to lie at the horizon of the black hole. So I'll do that, and I'll send it to Steve through email, and then he can propagate to you. But yeah, I don't really know. I know like a pulsar, typically a very fast spinning pulsar can, at the surface, it can go at something like 15% the speed of light. And I suspect that a spinning black hole would go even faster, but yeah, of the same mass, but I don't know the number, I'm afraid.
Okay, right. I did say that was the last question, but Tony Morris has been waving at me for about 10 minutes, so I'm going to let him go, but I think we should call that the last question. So, Tony.
Thank you very much, Paul. We're checking the post.
That's fine.
Rene, just carrying on from what Roy said, if a black hole is infinitely small, sometimes in the popular press you get the equator of a black hole and its spin axis. So do they affect the size of the photon sphere, the way it spins?
Yeah. I didn't get into that because basically it's at least a full semester of probably late undergraduate degree of physics or maybe PhD even. But basically, yeah. So if a black hole spins, the horizon of the black hole will actually not be a sphere, but it would be a bit, oblate. It would be a bit squished. And then there's even a new zone, right? There was this last stable orbit, and then there was the Photon Sphere. There's even another horizon that appears for a spinning black hole that's called the ergosphere. So I won't get into the details of that, but yeah, it changed. So there is a change of shape, and so the black hole will be basically like larger at its equator than at its poles, like the horizon, basically. So yeah, that's absolutely right.
Thank you.
Okay.
By the way,
carry on, Rene.
Yeah, I was just going to say, so I posted a YouTube video in the chat. I'll send it also to Steve to pass on to everyone, so you can check it out after the talk. But that's basically a journey into a black hole. If you've got like a VR, goggles, you can even put it and like pan around. But that's like the sort of like projected like 2D version. So imagine that there was the black hole at the center. Well, you're basically going towards the black hole at the center of the Milky Way, so you have like the full sky, and then do you see it being animated, or it's just
yes, we do.
Okay, because I don't see anything on my end. I don't see it moving, but yes. So basically, okay, I'm not sure where you're at. Okay, yeah, we can see it. Yeah. So as you approach closer and closer to the black hole, right, you can see the shadow of the black hole, right, because light cannot come from it or anything that's behind. But also light, right, that travels at grazing angles near the black hole, right, gets distorted, right? Just like I was talking about earlier, answering one of the questions. If light travels, right, it might be deflected. So you tend to get like this ring around the black holes, because of light, either from the background or from nearby that's emitted, tends to be deflected. And these sort of things, right, for massive objects, like massive galaxies or clusters of galaxies, you can see. So we call them gravitational arcs. So when you look at distant galaxies, sometimes you see arcs around there, or multiple images of the same object. And that's because of that distortion of the space-time. And then we carry on closer and closer, and then closer. So I'll just like speed it up a little bit. And then you get closer to the black hole, and everything becomes more and more distorted. And then now you have like, projection effects, right? So it's a bit annoying because we're kind of like stuck on the, the sort of like squarish, shape of this. But if you, sorry, I'll just share my browser instead, because when you view it into the, I think, yeah, when you view it on the website, okay, well, I think I picked the wrong one, but I'll try and share the other one. But you can basically pan around, and then, well, this one is not the exact same video, but when you pan around, then you can see that as you get closer and closer, everything becomes dark, except, you know, that cone of light that I was talking about, you know, if you look backward. And then eventually, only light that travels exactly perpendicular can escape. So the observer that falls into the black hole would see the same thing. All light that comes from the sky will come closer and closer from one single point, until basically, as they reach the surface of the black hole, all light comes from the entire sky is beamed into this one point that's above, like towards the outside. So it's really mind-boggling.
Well, yeah, I look forward to exploring that a little bit more closely. Rene, thank you for an excellent evening. It's been totally engrossing. I'd like to ask people to thank you in our usual Mexborough and Swinton manner. So thank you very much, Rene, and I hope that you're going to be able to come and visit us at some stage.
Yes, I would be very much pleased to it. Yeah.